various properties of the crystal. So how we are going to study that? By using either X-ray, electron beam, or the neutron beam. So now what we are doing here is that we are incidenting the X-ray here on the surface of the crystal, and we want to study the properties of the crystal. So how we are doing so? So let us have a very clear, in detail information regarding the diffraction through crystal. So here the light rays when passes through the so what is actually the meaning of diffraction? First, see we want to study the different properties. So how we are studying? By incidenting the X-ray on the crystal. So the crystal's structure properties can be learned by incidenting the light ray X-rays, right, on the surface of the crystal. Now what character of light we are using here? So we are taking the help of a diffraction. So what is the meaning of a diffraction, and what is the condition at which the diffraction occurs, and how these diffractions are uh, are affected on the crystal? And also at the end we just discussed about the X-ray diffraction in crystals. So what is actually the meaning of diffraction? Everybody is having the idea that the diffraction of light is in a character of the light, right, which is exhibiting the wave property. Now the light rays, when they are incident at the orifice of the object, at the end surface of the object, or we say that the bending of the light ray at the edges of the object, that is known as the diffraction of light, right? Now so this is actually the meaning of diffraction. And what is the main criteria or the condition for which the diffraction is occurring? So what is that condition? The always we need to remember that the basic condition on which the diffraction occurs, that is the thickness of the obstacle or the slit, is should be incomparable with the incident light wavelength. So this is the basic condition on which the diffraction occurs, right? So here we need to understand also what is actually we want to move towards the Bragg's equation, what you have studied in chemistry in the intermediate, right? So first of all, now since you are having an information regarding the diffraction, on what is the condition on which the diffraction occurs, and what is this diffraction in crystals was introduced by whom, right? In the year 1912, a German physicist Loy suggested that the three-dimensional arrangement of the atoms in a crystal can produce the diffraction, uh, and this diffraction should be with respect to the radiation, right. So but with the radiation, and how this X-ray diffraction in crystal is taking place. So the wavelength of the X-ray should be in the order of the angstrom, which is also the range of the interplanar spacing between the atoms inside the crystal. And if this is the condition, then your X-ray diffraction will occur. And why we are taking X-rays only? Why we are not talking about electron beam or neutron beam? Since X-rays are having a very less wavelength, right? So the one angstrom is equal to how much? 10 to the power of minus 10 meters, or 10 to the power of minus 8 centimeters. And this wavelength is incomparable with the spacing between the atoms inside the crystal. So until now we just studied the previous information regarding the diffraction in the lower classes, in the intermediate. From the intermediate, a student should know that what is actually the meaning of a diffraction and the diffraction in the crystal. So now onwards, whatever we are going to learn, we'll just move on to our main topic now. So here, so now you already know that diffraction, how the X-rays will be produced. We just recalling what we studied in the lower classes. So you can just see this schematic diagram where you can see that there is a typical X-ray tube. You can say X-rays are produced whenever a high speed, you can see high speed, high speed electrons are colliding here, colliding with the metal target and source of electron. Here the electron, this electron source is the hot filament, which is a high accelerating voltage. You can see this is a high accelerating voltage between the cathode and the anode. So the metal target which we are talking about, that may be copper, aluminum, or magnesium, which is acting as the anode. Now this is the way how the uh, X-rays are produced, right? So now Bragg's equation, you already know that this is the condition. If this condition is satisfied, then only your X-ray diffraction will occur. We say that that is called Bragg's equation, right? So who is the scientist who discovered this Bragg's equation? So what is Bragg's equation in mathematical form? That is 2d sine theta is equal to n lambda. So the English physicist, that is Sir. Why we say Sir? Because he is a scientist who won the Nobel Prize. So the persons who won the Nobel Prize should be referred as Sir. So Sir W.H. Bragg and his son Sir W.L. Bragg developed a relationship in the year 1913 to explain why the cleavage faces of the crystal appear to reflect X-ray beam at certain angle of incidence, right? What is this meaning of why the cleavage faces of crystal? So the exact nature or the character of the crystal will be seen when the X-rays are incidenting on the crystal, and this incident angle will be at a particular angles only. This particular special property can be viewable. So you can just see that the distance between the atoms, uh, between the consecutive atoms which are residing, as we said, that the lattice planes, right? I will show you the figure also. And the variable lambda is the wavelength of the incident X-ray beam. And see, we're just discussing in the second paragraph the what is n lambda and d, right? So the d is a variable, and which is the distance between the atomic layers in the crystal, and you are having the wavelength. Lambda is referred to as wavelength of the incident X-ray beam, right? Now, so the observation here is an example of X-ray interference, wave interference, commonly which is known as X-ray diffraction, and we say that XRD, and which is the evidence of periodic atomic arrangement or the structure of the crystals, right? So here the XRD is nothing but X-ray diffraction, and this X-ray diffraction is occurring by the phenomenon of interference, right? So you can just see that constructive and the destructive interference. You can see how the wave look like when it is constructive interference, and how the wave look like in schematically the destructive interference, right? You can see what is how we say that the constructive interference are in phase and the destructive interference is the out of phase, right? So now with this uh, right? So with this, we can just say that the information of the constructive and the destructive interference of waves, which is occurring, right? So here, Bragg's equation, you all having the information about Bragg's equation, that is 2d sine theta is equal to n lambda. Now you can just see that these atoms, the atoms are arranged in this particular format, the layer of consecutive layer of atoms, and that is the reason that we just have a dotted lines here. So when the X-ray beam is incident on the atomic layer, so this is first atomic layer and this is the second atomic layer. So when the X-ray beam, some X-ray beam will be incident on the first atomic layer, and they are getting reflected back, right? And the some rays, X-rays, will go inside the uh, crystal. The second, we just take an example of the second atomic layer like this. Some of the X-rays will travel to the third layer and fourth layer and so on. So for our comfortableness, the Brax has given us the information, right? So only about the two atomic layers and how these two atomic layers will conclude to the Brax equation. You can just see this, the first ray, X-ray, is traveling, right, in this particular format. So here the second ray is traveling extra. So what is that length which is traveled by the X-ray in the second incidence at the second atomic layer? The distance is given here very clearly. It is given, see, it is given as ABC. This is the angle theta, and this is also the angle theta. So here, see, constructive interference, you already know that when the constructive interference occurs, when the path difference is equal to n lambda. This is, you just studied this in Young's double slit experiment. In the same way, here the path difference, whenever the constructive interference takes place, so how this constructive interference can be given as path difference is equal to n lambda. So path difference here, see the extra path which is traveled by the wave, the second X-ray wave with respect to the first X-ray. What is that extra path? AB plus BC. So n lambda is equal to path difference AB plus BC. We have written here. Since here the distance of AB and BC are same, so what we are writing, we can just write that AB is equal to BC. So n lambda is equal to 2AB. Here AB is there. AB can also be equal to, approximated to BC. So therefore we written here 2AB. So here uh, now, since this is the angle, so we just taken the right angle triangle. You can see what is the right angle triangle we have taken. See here, this right angle triangle, right? You can see AZB, AZB, AZB. The angle here, you can just see this this type of right angle triangle we have taken here. So sine theta, see, so sine theta, this will be your opposite side. So what is sine theta? Opposite by hypotenuse. So what is opposite side here? AB. See, the side which is opposite to the angle will be taken as the opposite side. So therefore we have written here sine theta. So sine theta is nothing but AB by hypotenuse, that is small d. So sine theta is equal to AB by d. So AB is equal to d sine theta. And you all know that n lambda is equal to AB. So we got the from the geometrical figure, AB value is d sine theta. So therefore we have written n lambda is equal to 2d sine theta. So lambda is equal to 2d hkl sine theta hkl. Now this is the way how the Bragg's equation can be mathematically evaluated. You can just see this figure. So with this figure and with a very basic idea regarding the or the concept of the Young's double slit experiment and the path difference, we can just deduce the Bragg's equation, right? So with this, I think that you got very clear idea regarding how this Bragg's equation mathematically can be written as n lambda is equal to 2d sine theta. You can just see this, the X-ray diffraction methods by which we can know the different properties of the what you can say crystal. So law A method, powder method, and rotating crystal method. These are the different methods of X-ray diffraction by which we can know the exact structure of the crystal, and also the different by which we can know the different properties of the crystal. In the syllabus, since in the syllabus it is given only the powder method, so we just go for the powder method, right? So we are not concerned with this uh, Loy method or rotating crystal method. That is also one of the method, right? So what we are taking in the powder method, so you can just see that very fine powder sample, it may be single or polycrystalline crystal is used to, instead of here what we are taking, a polycrystalline crystal is used instead of the single crystal. So here you should remember that we are using a polycrystalline solid in the powder form, and this powder sample is you can say we can this can be oriented in the different direction. I will show the figure how this is oriented. When the X-ray is incident on the sample, a sample holder is there, and inside that sample holder we are putting the polycrystalline powder by means of an adhesive, and we are incidenting the X-ray, right? So when you are incidencing the X-ray, so you will get different orientations of the what you can say X-ray beam, which can be known as the set of planes which are present in the powder sample. So how we can know that different orientation? By means of a DB Shearer camera. By using this DB Shearer camera, we can locate the different lattice planes which are oriented in different direction. You can just see a small amount of powdered material is sealed into a fine capillary tube made up of glass and does not which does not diffract X-ray. Right, the sample is placed in the DB Shearer camera. DB Shearer type of camera, right? So in the previous 19th century, so DB Shearer camera is used, which is actually aligned in the center of the camera. See, we are just placing the sample exactly at the center of DB Shearer camera, and the X-rays, as the X-rays are entering through a collimator, I will show you the figure. So the it will made to incident on the sample which is inside the capillary tube, right? So at different angles, you will get a picture of different orientation of lattice planes. The powder diffracts the X-rays in accordance. The diffraction takes place in accordance with the Bragg's equation, and as the Bragg's equation is getting satisfied, you will get a diffracted beams. So now you can just see that this is the way. See, this is a sample holder, and the sample holder, and this is the cylindrical cassette, right? DB Shearer cylindrical cassette, and here we are incidenting the X-ray beam. Now, since the X-ray beam is incidented and on the sample, which is residing in the center of the cylindrical cassette of the camera, so the X-rays will incident, right, on the polycrystalline sample, and they will get oriented in different direction. With, you can just see this is type of orientation in the form of a cone which is impinged on the cylindrical film, right? There is a thin film cylindrical. We just say that this is cylindrical cassette. In the previous days, in the camera, we used to have a film, right? By which we'll develop the film, and that is called negative film. The same manner, you are having a film, and here the sample orientation at different angles will be impinged. You can just see you get a curve cone like shape at different angles. You'll get the this type of symmetrical cones, right? So when the film is here, the cones intersect strip to a photographic frame which is located in the cylindrical camera to produce a characteristic set of arcs, right? We just say this is arc, and when the film is removed from the camera, they show the diffraction lines and the holes from the incident and the transmitted beams. You can see for a sample of several random, you can see first the sample is of a polycrystalline solid. There's a polycrystalline solid. You can get a front reflection and back reflection. So for a sample of several random oriented single crystal, diffracted beams will lie on the surfaces of, say, different cones, right? In the case of powdered sample, the diffracted beams from form a continuous cones, right? So now with this, we can just say that this is the shape, symmetrical shape, right? Determination. See, by means of powder method, we can just determine the lattice parameter of the given polycrystalline solid by using the given formulae, right? You can just see that the distance here from here, see, you can just see this distance is considered to be S1, and this distance is considered to be S2, and the entire distance from here to here, we'll just take it as a W, such that we get the theta is equal to pi by 2, and so on. So what is the use of studying this determination of lattice parameter, right? So in the notes also, when I give you notes, you'll have a very clear idea. So with a different mathematical values, you can just see that you can easily understand by means of determination of lattice parameters. So what actually we want to gain from this X-ray diffraction technique. So this X-ray diffraction technique is used to compare or distinguish between the crystalline and the amorphous materials, right? By means of X-ray diffraction, we can know that the given crystal, which is in the shape of the powdered form, either it is a crystalline or the amorphous when you go for this X-ray diffraction technique. And by means of this X-ray diffraction, you can also know the exact structure of the crystalline materials, and we can just determine the how the electrons will be distributed within the atoms and throughout the unit cell. And we also locate the orientation if it is in the form of a single crystal, or else we can know the texture of the polycrystalline materials, and by which we can exactly measure the strain and the grain size which are existing in the polycrystalline solid. Now this is the various examples of X-ray diffraction. Now where actually this XRD is used and what are the advantages and disadvantages, right? So XRD is a non-destructive technique which is least expensive and which is used to determine the crystal structures, by means we can know the properties of the crystals. X-ray are not observed very much by air. You can know that X-rays are, since it is having a dimension of 10 power of minus 10 meter, so samples need not to be evacuated chamber. So you cannot we don't require any evacuated chamber here. While we do the experiment, mostly we have an evacuated chamber. Since X-rays are not observed by the air, this is the most important advantage of using the X-ray diffraction. And what are the disadvantage? You can see X-ray do not interact very strongly with the lighter elements, definitely which is present in the air. Now, so the lighter elements, you can just see that this is one of the disadvantage of the X-ray diffraction. So now we'll just see, this is what we have learned in today's class is Bragg's equation and X-ray. First we just discuss about diffraction and Bragg's equation, right? And then we have gone for the X-ray diffraction techniques of the methods, and in that method we discuss about the powder method, since we are having law and rotating crystal method. Since in the syllabus we have only the powder method, so we just discuss about the powder method and what are the advantages and disadvantages. Now with a video, right, we'll have a very clear idea. If you have understood a little bit, so then you'll have a very clear. Students, let us watch the video of the topics whatever we have discussed. So we'll back to back we'll have two videos about X-ray diffraction and Bragg's law. Let us watch. Now we'll just see the second video for a better understanding. So let us see the second one.
What is X-ray diffraction, and what is it used for? In an X-ray diffraction experiment, a sample is placed into the center of an instrument and illuminated with a beam of X-rays. The X-ray tube and detector move in a synchronized motion. The signal coming from the sample is recorded and graphed, where peaks are observed related to the atomic structure of the sample. Most materials are made up of many small crystals, like sand on a beach. Each of these crystals is composed of a regular arrangement of atoms, and each atom is composed of a nucleus surrounded by a cloud of electrons. It's at this scale that the story of X-ray diffraction begins. X-rays are high-energy light with a repeating period called the wavelength. Since the wavelength of an X-ray is similar to the distance between atoms in a crystal, a special interference effect called diffraction can be used to measure the distance between the atoms. Interference occurs when X-rays interact with each other. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the electrons. Electrons occupy special energy states around an atom. Since this is not enough energy for the electron to be released, the energy must be re-emitted in the form of a new X-ray with the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms form distinct planes separated by well-defined distances. When the atomic planes are exposed to an X-ray beam, X-rays are scattered by the regularly spaced atoms. Strong amplification of the emitted signal occurs at very specific angles, where the scattered waves constructively interfere. This effect is called diffraction. The angle between the incident and the scattered beam is called 2 theta. In order for constructive interference to occur, the scattered waves must be in alignment, meaning that the second wave must travel a whole number of wavelengths. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 on the scattered side, yielding 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered side, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs can be determined from the red triangle. The angle at the top is theta, half the angle between the incident and scattered beams. The long side is the distance between the atomic planes, and the short side we know is 1/2 of a wavelength. The relationship between the diffraction angle and the spacing between the atoms can be determined by applying the sine function. Rearranging this equation yields an equation commonly known as Bragg's law, named after Sir William Henry and William Lawrence Bragg, a father-son team who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. This technique of X-ray diffraction is used today for a wide variety of materials, ranging from single crystal epitaxial thin films to polycrystalline mixtures of powders, and even randomly oriented amorphous materials. X-ray diffraction helps scientists to develop new pharmaceuticals, classify rock formations based on their mineral components, and understand how the arrangement of atoms affects the behavior of energy storage materials. As scientists push their ability to engineer materials on the atomic level, X-ray diffraction becomes an increasingly important tool in their toolbox. Advances in equipment design have made X-ray diffraction easier to use and more powerful than ever.
Right. I think that you have understood, student. With this, we'll just end our today's class. That is part 2 of engineering physics, class 6.